Well, hello. We're doing Unit 1, Answer 5, Part 2, so talking about behavior of gases. And this will relate back to the pressure, weather pattern things that we saw a lot and hopefully help you understand those a little bit better. So, density is an important part of gases because they are much lower density than solids and liquids because the distance between the particles is much bigger. The reason why they have such low density is because their particles have more energy, which means they're moving a lot faster. So gases, just like liquids, are considered fluids, which means they flow past one another. And that's really the capacity of them to flow. So that's what allows like wind to happen. You go from high pressure to low pressure. Particles are moving to balance out those pressures. So when you get those pressure systems, remember high pressure and low pressure, which is related to temperature of the gases. That gives us the certain weather patterns that we see, the wind patterns that we see, and because of the uneven heating on the Earth, we have the cells, the Hadley cells and such, that help us determine weather patterns. So, here we go. So imagine you're filling a syringe with liquid and you try to compress it. So you're doing the same thing with a liquid. It's not going to compress, right? Or if it did, it would be so small you wouldn't notice it. But if I fill a syringe with gas and depress it, the gas would compress. And when that happens, so I go from this spot, so the very spread apart to much closer together, we say that the pressure is increasing. Think about just simply the amount of collisions that's happening. They're not going to bump into each other a lot here, but when they get closer together, they're going to bump into each other a lot. That means that's what pressure is collisions of gas particles. So here I look at the low and high pressure one. The low pressure one, particles are really far apart, less collisions. Particles are really close together, more collisions. Hey, pressure is related to volume, which is what I see here, high volume, low volume. It's also related to temperature, and we'll talk about that more in the future. So Earth's atmosphere, which is known as air, is actually a mixture of gases. So it's mainly nitrogen and oxygen, but we have other gases in there as well. But because you don't feel air, we often think of them as not having mass, which is not the case. So last week when we did the conservation of mass lab, when you opened the water bottle that had the Alka-Seltzer tablet in it, the gas that was produced in that reaction was able to escape out the top, and then the mass should have decreased. It would have been a ton, but the mass did decrease. So gases do have mass. So if I look here, closer to the surface of the Earth, there's more gas particles, so there's more collisions, so we have higher pressure. And when I have higher altitudes, there's fewer gas particles, and that means that there's lower pressure. So as gas molecules are pulled closer to the Earth, they collide with each other in the Earth more often. That causes air pressure. So pressure is force or weight over area. So the more particles there are, the more force there is. So pressure is increased. So to find pressure, you need to know force and area. And there's many different ways that we can measure pressure. One such one is pascals. But it's such a tiny, small unit that we use kilopascals, or kPa, which is 1,000 of these. So just like kilometers is 1,000 meters, and that gives us something that we're able to measure. So atmospheric pressure can be measured with a barometer, which is just a tool that we'll look at. So the first one was just like a liquid mercury sitting in a dish, and the more collisions that force down on it, the higher the mercury goes in. So the more air pressure there is, the higher the number is, and that means that we have really dense air, right? And then that means that we can predict the weather, right? So mercury settles to a point where the force of gravity is equal to the force of the air pressure, and then that is your air pressure. So at sea level, the average height of the mercury is 760 millimeters high. So 760 millimeters, that's like 0.76 meters, right? Got to move it 3 spots to get back. So we say that 760 millimeters is equal to 1 atmosphere of pressure. So the weight or pressure of one of our atmospheres. We also call millimeters of mercury torr because of the dude who invented the barometer. So that means that we have many different ways to measure pressure. So we have 1 atmosphere, which is equal to the average height, which is 760 millimeters of mercury, which is equal to 760 torr, named after himself, because if you invent something, you have to name it after yourself, which is also equal to 101.325 kilopascals, which is our average, which is our SI unit of pressure. And then PSI, got to have our English measurement, pounds per square inch. We can't have science without throwing in one random English measurement or US or imperial system measurement. And so that means since we have all these equivalent values, we have to be able to convert between them. So this is maybe the more difficult part of the unit for most people. So sample problem A, current pressure in Minneapolis is 774.7 millimeters of mercury. Current air pressure in Miami is 1.1 atmosphere. Which city has higher pressure? So if I were to look at that, what I want to do is I want to take 1.01 atmospheres and I want to convert it to millimeters of mercury, mmHg, okay, to be able to compare them. Okay, now to do that I need to lay out a conversion factor that looks like this. Whatever units I start with go on bottom. So that's atmospheres. Whatever units I want, in this case millimeters of mercury, go on top. And then I look up here and I see that there's 760 millimeters of mercury for every 1 atmosphere. And this is just like multiplying fractions, like if this is over 1. So it'd be 101 times 760 divided by 1, which would give me, forgive me while I pull up my calculator, 1.01 times 760 gives me 767 millimeters of mercury, which is lower. So that means Minneapolis today has, Minneapolis today is the city with the greater air pressure. Okay. So that was hypothetical. So, if you were to look at your weather app on your phone, one of the things that you'll see is they actually do list the air pressure. So as I pull open my iPhone, I'm just going to go to the weather app, and it says that I have 29.75 inches of mercury. Okay, again, because we're not the metric system, we measure things in inches, not millimeters, which is so stupid. Okay. So what that means is that I have to convert that to something that makes sense, like millimeters of mercury, something that we use everywhere else, right? So that means I have to do another conversion factor, and anytime I'm converting, the units that I want go on bottom, inches of mercury, and in this case millimeters are going to go on top, and in this conversion factor 1 inch is 25.4. So I'm just going to multiply here, divide on bottom, and that's a plus sign. I'm going to divide. So all I do is my calculator, 29.75 times 25.4 divided by 1. Now in this case it just so happens that would be 750, I'm going to round it, 6 millimeters of mercury. Okay. So one thing to note is that this conversion factor process is kind of the basis for us. It's just helping us make sense of all the different pressures there are. So what I want you to do is pause here and read this really quick about how the kinetic molecular theory helps us understand pressures, and then we're going to talk about it on the next one. So pause here quick and read over it. All right, so how does that help us explain pressure? So air particles hitting the edge of the containers creates force. So as the air pressure hits that wall of a container, that's force, that's pressure. The more particles there are, or the faster they move, the more pressure there are. So imagine there's only one particle and it's moving really fast, it'll create some pressure. Say there's a lot more particles, but they're hitting it slower, maybe you have equivalent pressure. Who knows? You have to be able to measure all of it. So as a related question, why do your tires get flat in the winter? What happens to temperature? Well, the temperature drops in the winter. So it's not necessarily, although there are some leaking, there is some inevitable leaking that happens as you're driving. But in general, the particles, if this arrow is the speed, in the winter, that arrow would just be way smaller, which means it's not going to hit the wall as hard. So in order for us to have the same air pressure to support the weight of your car, you have to have more of these little arrows, like more air particles, in order to balance it out. So that's just one thing you see with air pressure. So before we can study gases, we need to know about moles. So this is an idea that's with us in the second semester a lot. So what is a mole? 1 mole is equal to a certain number of atoms. It's always that number of atoms, which is a really big number. But specifically for gases, it's 22.4 liters of gas. It's also equal to a mass. So this is a way for us to count really small particles like atoms. Because if I said, hey, go grab 5 atoms from the lab, you'd be like, well, I can't because atoms are tiny. And be like, okay, go grab 5 moles of labs. Now all of a sudden I have, or something from the lab, now I have a volume or a mass that's measurable. So how many particles of carbon dioxide are in 2 moles of gas? This is the same thing as what we did before. So I have 2 moles, right? And I want particles. That's going to be the final answer. So particles, I'm just going to put P here. What I know is down here, I have moles to cancel. And then particles, P, will be on top. So notice it's 6.02 atoms, particles, or molecules. 1 is with moles, so 1's going to go down here. And 6.02 times 10 to the 23rd is going to go on top. Now, in your calculator, it is probably smart. There's a different way you could do it. You have to put all of this in parentheses, though. Otherwise, when I do it, order of operations is going to be messed up. And then my answer will be 1.02. This will be 2 times what's on top divided by what's on bottom. Okay. If there's another sample problem, hold on, I'm going to pause really quick. So here's the second sample problem. Now notice, the one thing to note is that no matter what type of gas it is, it doesn't matter because it's the same number of molecules, right? So I could have 2 moles of CO2 or O2, but if I want to convert it to liters, it's the same. Moles will go on bottom to cancel, liters will go on top, and it's 22.4 liters per mole. So 2 times 22.4 is going to be 44.8 liters. Okay. So now here, 1, 2, 3, 4, and 5. You got 5 practice homework problems. When you're done, submit. Tomorrow there will be a video walkthrough of it, so just do your best with it and then check the key tomorrow. I will not give you full credit if you submit tomorrow because you'll have the key accessible. So do your best, ask me a question. Quick note about this one right here. Or this one, sorry, 36 liters. Be careful. That's 36 liters. When I do this, which side is liters going to have to go on? I want moles, so moles is going on top. So make sure you realize that 1 mole is equal to 22.4 liters, so 22.4 has to go on bottom. And this means you have to divide by 22.4. Okay. Good luck. Let me know if you have questions. Bye.